Okay, Brian Miller-Hicks here, continuing our series of narrative PowerPoints for engineering geology. So we have a building site, project site. We've done a geologic soils investigation. We've discovered ground conditions, whether they be clays or unsuitable soils, what have you. So the next task or series of tasks is to prepare the ground to make it more suitable for construction, whatever it is, building, bridge, roadway, etc. So that may involve, and often does involve, a process called grading, in which landscape is reshaped, the ground is reconformed, excavated, improved, conditions are mitigated in order to make the site friendlier for construction of your project. So here is a picture of a canyon cleanout in the city of Oceanside near a school. You can see here in these layered silts, this was an old pond fill full of silts that had to be removed. And so the canyon had to be dug out, excavated, and replaced with more suitable material. Okay. So grading, it can involve a lot of things. It can involve the removal of expansive clays. It can involve landslide repair, improvement of slopes, whether they're cut slopes or fill slopes, something to improve the underlying masses of soil and rock, make them more amenable to construction, as I've already said. So it's land modification. You may end up building pads for homes or buildings, flat pads. You may put in slopes, cut slopes or fill slopes. You may put in roadways. So here we go. What are the duties of the engineering geologist pertinent to site grading? I'm not going to go through all this in detail. You can read this for yourself. You or your firm have to be approved as a geologist of record. You have to have signed contracts. You need to review the soil or geotechnical report before grading actually begins. This is extremely important. You need to know what the recommendations are, especially if you didn't do the investigation yourself, if another company did it. Oftentimes, you'll find this as a practicing engineering geologist, the contractor that's doing the grading hasn't adequately read the report or doesn't adequately understand the report. So it's up to you to fill the holes and to make him aware of site conditions and recommendations for improvement. That ideally can take place during a pre-construction meeting to discuss excavation, grading, shoring, walls, paving. You want the site superintendent there, you want the owner there, you want the client, architect, everybody that's involved with designing and building this project should be there. I need to tell you, often, especially with small projects, you don't have pre-construction meetings. All of a sudden you get a call a day after or even the day of, hey, we're going to start grading this site. Do you want to come out to look at what we're doing? And we're going, yeah, where's the pre-construction meeting? Of course, by then it's too late because they've already got equipment on site. So you do your best to go in there and present pertinent information. Okay? Lines of communication are very important during grading of a project. Make sure everything's done right. A lot of projects, the city or county may require the engineering geologist to be on site full-time. Not all projects. Some projects just part-time should be adequate. But sites that are large and sites that have critical issues, it's often recommended that you have a full-time engineering geologist. So here's a picture of a construction trailer where you're all going to meet, all the designer, architect, etc., in a nice air-conditioned trailer, and go over all this stuff I talked about in the previous slide. Okay? So You have done the geotechnical investigation. You have a copy of the geotechnical investigation report. You have the recommendations that go through excavation, shrinkage, and expansion of materials. That means when a let me put it this way, when a firm, dense soil is excavated and then put back as compacted engineered fill, it'll undergo, it won't have the same density as it had before. So in that sense, it undergoes a volume change. It may be less volume than, more volume than was originally there. You can pack more dirt in because it's not packed quite as tightly. So you got to deal with the quantities of earth, whether you need to import or export materials. If the material expands when it's put back in, like you have solid rock and it's broken up into pieces, now the volume is expanded. So the question is, where do you put the excess rock? Okay, that figures in, not everywhere, but on certain sites. Of course, you have to remove trees, vegetation, trash, old structures, pipes, leach fields, all that has to go and disposed of off-site. And during site grading, two basic operations, cutting and filling. You can look at a hillside, you can cut on the high side and take that material that's cut away and put it on the low side of the hill so that you have a flat pad. That leaves you with a cut slope on the higher uphill side and a fill slope on the downslope side. The fill slope is composed of fill, and the pad may be composed of fill as well. You're going to set your building on top of that filled pad. It's important to get proper compaction of that filled material, and there are standards for compaction. You take a sample into the lab and run what's called a Proctor compaction test, and you do it at different moistures. If the material is too dry, it'll have a low density. If it's too wet, it'll have a low density. So you want to look for a maximum density and an optimum moisture content. So that's what you want your compacted fill to be, is 90% of that maximum density under optimum moisture conditions. Usually clays will take more water than sands because they absorb more water. Okay. Issues during grading. I've kind of touched on these already, but you have slopes, whether they're natural or artificial, steep or gentle. You have landslides, maybe. These are very critical and tricky geologic phenomena landforms to deal with. You have faults. You may have inactive faults, which are not treated as equally as active faults. For active faults, you may have construction setbacks where you have to set buildings away from the trace of the fault 25 or 50 feet. With inactive faults, you don't have the issue of failure and generation of earthquakes, but they can act as conduits of water, and they can also contain sheared clays and unsuitable material, which may have some issues that you might deal with during grading. Groundwater, high groundwater is always an issue. Raveling soils. Raveling means dry rolling of grains of dusty sands, loose sands, etc. on a slope. Then you may have done your best during the investigation to assess conditions, but often during grading, you can run into unexpected conditions. Old buried structures you didn't know were there, clay pockets, seepage of water, undiscovered strata, undiscovered, unanticipated conditions. That all can hopefully be dealt with during grading. All these conditions require your attention and mapping if you're the engineering geologist on site. So what do you do before you actually start grading according to the grading map, grading design that is generated by civil engineers and architects. You want to get rid of all undesirable materials. You dispose of those materials off-site. And the engineering geologist may be called to determine which materials are undesirable and should be removed, which materials maybe you can mix with suitable material. That can happen too. Remedial grading, this goes into more detail on mitigating conditions of soil and rock which are unsuitable and bad for your project. So you can remove loose soils. Undocumented means old filled ground that hasn't been tested, that may not have met optimum density or maximum density, optimum moisture conditions. Alluvial or water-laid soils. As I said, some material may be reused. This paragraph is important. So in that scenario I discussed where you cut the high side of a hill and fill the low side, you have a cut, you may have cut down the formation on the high side, and so the rear of the pad, building pad next to that cut slope may have formational material on the surface. And then you go across the pad and you may have fill material on the downhill or lower part of the pad that sits on the downslope side of the hill. So that means you've created a transition from formation to fill, and you have a line going through maybe the middle of the pad. So you have, let's say, sandstone on uphill side and fill on the downhill side. If you don't do anything and you set your building on top of that transition line, you may have differential settlement where the fill settles, let's say, an inch over 50 years, and the formation settles less than that. So you may have differential settlement, which can cause distress in your structure. To prevent that condition, you undercut the cut side, remove a couple, 3 feet of formation, and fill that back in with a compacted fill. So now you have a uniform fill pad all across the pad itself, so that you have uniform foundation conditions. Okay. So engineered fill, as I've already discussed, you need to compact it to 90% maximum dry density. Below pavements, you may require 95%. So the compaction testing of fill during grading operations usually handled by soil technicians, but geologists can also do that and also can keep an eye on practices of filling. You got to compact under the structures and 5 feet around the perimeter of the structures at least. Place the fill in thin lifts, moisture condition each lift or layer as you go. Here's what a soils technician can use to test engineered fill. This is compacted fill under here. He drives a stake through this plate and punches a hole in the fill, usually 6 inches or so deep. Then he sticks this nuclear gauge with a probe that goes into the hole. The probe has a radioactive element, cesium usually, that gives you readings of moisture and density and gives you a digital readout, which then you record as % compaction. So it's really quick and fast and reliable. There's another way of testing compacted fill, old school, called the sand cone. I won't get into that here, but trust me, it's slower and it's much more labor intensive. And I did hundreds of sand cone tests when I was learning how to do all this stuff. Foundations. Okay, so we have a graded pad. We're ready to set a structure on top of the pad that's underlain by compacted fill or formation, pure formation in some cases. So you have to verify depths and widths, verify they conform to the report recommendations. Steel and concrete are checked by special inspectors. Deep footings, you want to check those for adequate depth of embedment into compacted fill or into formation. Okay. So here's a picture, simple photo of a simple residential structure with footing excavations having been dug out. Slopes. So here is a finished cut slope. You can see maybe that this has exposed rock in it, and I cover slopes and rock mass structures and joints and fractures in other PowerPoints. Here is another slope behind an existing residence I was called out to look at to see if we could improve this slope, because as you can see, some of it's sliding away. It was too steep. It was cut in sandstone with low cohesion, so it's sloughing and sliding as it gets wet. It probably should be laid back or removed and rebuilt as a slope with possibly a higher retaining wall. So faults can cross slopes, of course. This is one site in San Diego where the fault is running more or less parallel to the slope. So this isn't a finished slope. They're just excavating this to put fill in back up against the slope. But you'll notice this is the actual fault that I mapped and marked, and it turns out that this fault goes through sandstone, formational sandstone, which again is dense, but it's broken up by fractures that are parallel to the fault. And so when they're excavating this slope, these slabs were sliding out like so along these fractures. So that's a condition the engineering geologist has to be aware of, to note, and to give recommendations to the contractors as to how to handle this condition and improve the situation. Here's a fault mapped on a cut slope. This is the general approximate trend of the fault that I found. And here it is crossing the floor of the construction excavation. So this is really cool. You can actually see it running across the floor, and you can actually put that on your map and locate it pretty precisely if you have a good grading plan. So it's a clay-filled fracture plane or fault. It has to be mapped. Any fault should be mapped as encountered during grading. Here's another fault that I found, or actually a soils technician found this, and he called me out to look at it. You can see very clearly this is a fault where the bedding has been displaced. This sandstone, this white sandstone, should match up with this white sandstone up here, but the fault has displaced the sandstone a couple feet. It's old Eocene age scripts formation, and the fault is a bedrock fault that is old as well. It's not an active fault, but it does leave evidence, and as if a geologist has noted this, it should be mapped and defined. So here's my drawing of the fault features. Here's the bedding, the white sandstone here and the white sandstone here. Here's the fault trace filled with clay called gouge. Other features as you note here. So it's important to put this on the record, because that's your job as a geologist, to go out and map these things and draw them up. Downtown San Diego had gone through a building boom, which is still going on, of high rises in the downtown area. And because parking is so restricted in downtown San Diego, a lot of these high-rise buildings were built with subterranean parking garages, which meant you had to excavate 30, in some cases 50 feet down below existing ground level. So as you're doing that, as the excavation proceeds down deeper and deeper, you put in wood lagging between these steel soldier beams, so that this whole excavated material behind this wall is supported. But as a condition of this excavation during grading, because San Diego downtown is mapped as a possible earthquake fault zone area, the geologist is called out to map the strata, the sedimentary beds, and any fault features as you go downwards. The paleontologists love this kind of operation as well, because they get to discover and sample all kinds of cool fossils that may be exposed during excavation. So as you can see, before the wood lagging is put up against the wall, you have exposed strata, and you can map these exposed strata. You have to be there each day, every day while they're doing this, and make sure you stay ahead of the people that are putting in the lagging. Otherwise, you don't get to see it. So you got to get in there as soon as it's excavated, map this stuff. So here's a sketch or a drawing of one section of an underground excavation. Here are the steel soldier beams that are put in first, and the lagging, of course, you might not be able to see that. Each course of lagging is a foot wide, and you have really, really great mapping control here. You know the elevation that you're at any given point. You know the spacing between these soldier beams, and you know the vertical elevation change. All you need to do is count the number of wood planks that are in there to to get your depth, and you map every feature you can see. Down here, if you blow this up, you can see I mapped a paleosol. This is a hotel project in downtown San Diego. So that's all I have to say about grading and the engineering geologist's role during grading of a project. I thank you for your time.